Last time we basically talked about basic experimental design, and now we're going to talk about some of the other things taking experimental design a little bit further. And one thing I definitely wanted to talk about was sampling variability. So sampling variability is not bad. It's natural variation just due to nature. For example, if there was no variation, then everyone would have exactly the same type of hair. And we would have the same type of eyes. But some people have stray hair, some people have curly hair, and that's fantastic. So we have a lot of variety in nature, right? So when we're trying to compare differences, whether it's from an observational study or an experiment, it's nice to minimize that variation. And we're going to talk about one way we did it last time is by randomizing. So we did random assignment. And here I'll go to page 17 of the packet. So we did random assignment so that the groups that we created were roughly equal. Now, the thing that doesn't work, well, we're going to take this a little bit further and figure out how can we minimize that variation again. Now, what we also are trying to avoid, what is bad, is something called bias. So that's a tendency to overestimate or underestimate. It's not about variability. So what do I mean by that? Well, here's an activity, the random rectangles that we did back at the beginning of the unit. And this is traditionally what I see when I run it with the classes. Here is the guesstimate, which is biased high. And then here is the best judgment sample from my 7th period. And you can see this is where they got to pick, where you got to pick 5 ranked rectangles that you thought were representative. And most of you tend to pick the larger ones. When we did a random sample, we were the closest to the true value, which actually I can actually add in here. The true value was 7.42. So you can see here, generally speaking, the simple random sample on average will have the closest value to the true. Okay, now sampling variability, you can see the bias is this tendency to be high, but variability itself occurs with all 3 methods. So there's still variability in this random sample, simple random sample, just like the others, but it is unbiased instead of biased. So again, that's the importance of the sampling variability, of the difference between sampling variability and bias, okay? Another thing, when I was looking at your 1 in 6 games where you have to do an estimate, let me talk a little bit about, I rank it on a scale of 1 to 5. You get 100 regardless of your ranking. So what is a 1? A 1 is either you don't answer my question, or you just give me a very simple answer and you don't justify it. Okay, so that's 1 out of 5. 2 out of 5 is, for the example, the one we did earlier, we had 11 out of 100 were winners. And you end up comparing it to 1 out of 6, and you're like, oh, it's less than 1 out of 6. We don't have enough winners. So that's a scale, that's a 2 out of 5. So you're basically doing a very simple comparison. You're not doing any statistics. 3 out of 5, you're really starting to do some statistics. You're calculating the probability of getting the sample, kind of like the circle here, given our model. Okay, so here, this is an example with the simulation. If the probability is very low, less than 5%, then we say that's statistically significant, all right? So I think on this last one, some of you got 8%, some of you got 1%, because some of you had errors in your probability calculations. So even if you had errors, I still ranked you 3 out of 5 because you moved from the simple comparison to using some statistical tools, basically probability. Then if you could connect that to the correct conclusion, if you understood that a probability of 4% is significant, so we probably aren't making the right number of winners, okay? Or if the probability is higher, like 8%, that's not surprising. We're probably okay. we're like, okay, that sample's not that unusual. So it would be like right here, that's not that unusual. We're probably fine. We're kind of close to the expected, or not that far away from the expected. Then finally, you're probably wondering, well, what's a 5 out of 5? I've started to teach you some of what you need to get the 5 out of 5. So 5 out of 5 means that you're using the right model and you justify it. So we've learned a couple of distributions. We've learned binomial, geometric, normal, and the 1 in 6 game can actually be done with either the binomial or the normal. And you look at, did I meet the conditions? Can I use a normal distribution here? Can I use a binomial distribution here? And why? So it's calculating probabilities, which you'll later learn is called a p-value, and coming to the right conclusion and verifying that you are using the right setup. Okay, so coming here, that's all for this note on page 32. Something is statistically significant if it's unexpected, a probability of 5% or less. Okay, so then I have some examples, and then here we're going to probably play with this more in the next class, not today's. And this is how can you infer cause and effect, and who can you infer it about? Can you do it about a whole population? Yes or no? And is it just association, or is it just, or is it actually causation? All right, so now going on to our activity. So we have our answers. Actually, let me go. I was in the right one first. So we have our answers. Now this is the answers from one of my classes. So let me just start right here. Does type of SAT prep matter? So this is a StatsMedic activity. EKHS has decided to offer an SAT prep class again this year. It will be offered in 2 different formats, online or classroom teacher. The counselors want to know which teaching method will yield higher SAT scores, so they have allowed us to set up an experiment. 50 students have signed up to take some form of the SAT prep class, 20 seniors and 30 juniors. Now, don't worry about seniors and juniors right now. So the first thing they want you to do is outline a completely randomized design to compare the 2 treatments. So if you're doing an outline, that's fine. Let me go ahead and show you what our outlines look. That was back on page 17 of our notes. There we go. So there's a completely randomized experiment, right? So you could have drawn it like this. You got to say how it's assigned, all right? So some people go random. Now, when you do random, you really should give instructions on how to do that completely. So the idea is we take our subjects, which are the students, we could throw their names in a hat, mix well, right? And then draw without replacement for the first group. We could say, okay, we're going to draw, I think there were 50, so we would draw 25 names. And those first 25 names we draw, they go in group 1, and then we compare. So looking at this, it's actually better if you can describe it in words. So here we go, assign a unique number to each student. Could have done the names instead of unique numbers, but unique number is fine. It just adds an extra step. Put the numbers in a hat, mix well. Draw without replacement until you get 25 unique numbers. So I really love this mix well, all right? Unique numbers to each student. Notice how they said draw without replacement until you get 25 unique numbers. This is super clear. Assign these 25 to take the online course and the other 25 to take the in-person. Then compare the test scores for both groups. Gorgeous. All right, so now the counselors at EKHS think that the online versus classroom results could be greatly affected by the grade level of students that were put into each treatment group. Well, they know that seniors generally score better on the SAT than juniors, which makes sense, right? Although I'm going to tell you, I'm not sure if I would go with that. It depends, because juniors who come to take the SAT usually are like go-getters, right? So I'm not 100% sure I agree. I would bet on the juniors myself, but Unless, like, it's that mandatory, all the juniors take the SAT and all the seniors take the SAT. Yeah, if that's the case, yeah, the seniors will outscore the juniors. So how could you adjust your experiment to ensure that there is an even split of seniors and juniors in each class? Draw an outline of the experiment with your modifications. So one way we can minimize variability is by creating separate experiments. And we put our subjects in either the first experiment or the second. I'm not talking about treatments. I'm talking about completely different experiments, right? So we call that blocking. So if I go over here to your notes, this is from your E2 notes. We only really, on E2, we kind of just talked about completely randomized, but there are other types of experiments we can do. All right, there's some nice examples of terminology here, by the way. And what we can do, here I talk about why you can't just flip a coin. All right, and we'll get to that in just a little bit. Here is completely randomized. And then now, what if we think there's a difference, a big difference in the subjects, like sex, ethnicity, age, day of the week, whatever? Well, we can create something called a blocked experiment. Blocks are just multiple mini experiments where the subjects are, you throw the subjects together if they're similar. So here's an example from one of my students. He drew his block experiment. So you have 20 seniors, you're going to do random assignment, and then they either get group 1 online prep or group 2 classroom teacher, and then you compare the SAT scores. Then here's your second experiment, which we run again for the juniors. And then we list here, number the seniors 1 through 20, randomly generate 10 unique numbers between 1 and 20. These are group 1, the rest are group 2. And the same thing for juniors, except it's 1 to 30 and you're doing 15 unique numbers. All right, so now let's go to the next problem. Try and not look at the blue down there. Maybe I'll move that. Oh, I highlighted something. I don't want you to get too distracted by that. Okay, so the counselors are now worried that a student's GPA is certainly going to affect their SAT score. Let's look at only the juniors. So again, when you're trying to problem solve, it helps to simplify the scenario when you're trying to think, how am I going to do this? So if we're just looking at juniors, and we want to be sure that different GPAs are roughly evenly distributed into treatment groups, how could we be sure the GPAs are evenly distributed? So what might help first is to know the GPAs, and we could actually rank the students, which I think I'd rank the juniors from highest to lowest by GPA. All right, so we could do that. So now I've got my list. Highest GPA is student 1, second highest is student 2, third highest is student 3. All right. So if I were doing that, let's just say, here's my list, student 1, 2, 3, 4, 5, all the way down to, I think we had 30, right? So some people suggested, when we did this discussion in class, some ideas were, okay, well, maybe we take the first 15 and they do the online, and we take the second 15 and they do the classroom, right? Well, the problem with that is that the first 15 have a higher SAT score, right? So they're going to naturally be more different than the bottom. So in this case, we're actually increasing variability. So that won't work. And then they said, okay, how about if we do a block experiment where we put the first 15 in here? So try, pretend instead of seniors and juniors, you put top 15 here, create a block for them, and then the bottom 15 in the second block. That's a great idea. That actually will reduce our variability. The scores will be a little bit tighter. All right. And then I had another student say, well, what if, and I said, okay, we reduced our variability, and that's exactly the right direction to go into. What could we do instead? So someone said, well, what if we create 4 groups? Or just for the math, I'm going to say 5 because there are 30 seniors. I could say, okay, let's do the top oh, that won't work so well. Oh no, top 6 seniors, right? 3 go to online, 3 go to classroom teacher, then the next 6, etc., until you get to the last 6. All right, that's actually helping quite a bit. But could we do better? And finally, eventually someone says, well, the most groups, the more groups that we're doing on this, the less variability we're getting within our blocks. All right. So the more groups we do, the less variability in our blocks. Variability in our blocks. So what's the most number of groups we could do? Actually, I'm going to go ahead and do this right here. Sorry, guys. So what we could do is create the maximum number of blocks, right? The maximum number of blocks is 15. 15 groups of 2. So we would just basically have these 2 together, these 2 together, and these 2 together. So then the next thing is, how do I decide which person goes in which? Now, some people will sometimes say, oh, the odds will take the online prep, and the evens will take the classroom. And unfortunately, what that's going to do is it's going to introduce some bias, because the odd, 1 is going to be a little bit higher than 2. 3 is going to be a little bit higher than 4. So we're actually introducing a bias. So that's not a good thing. So we need to remember that when we're doing this, we want to do randomization. So let me go ahead and let me move this so you can read it now. So we rank the juniors from highest to lowest GPA. Make 15 groups of size 2 pairs, starting with the top 2 together down to the bottom 2. So every group has similar GPAs. For each pair, you can keep it really simple. You can flip a coin for the first student. Actually, there's more than one way to do this. You could flip a coin for the first student. Heads, they go into group 1. Tails, they go into group 2. Okay, I'm going to add an alternate method. Let me actually do it in a different color. An alternate method is I could flip a coin. Heads, student 1 goes into online. Tails, student 2 goes into online. So as long as you are randomly splitting them, so this is just an alternate, one of the students brought this up, then you are fine, okay? Let me see, let me make sure so this is all legible. All right, and boom. Okay, so now then basically what we did next is here's some of the big ideas. So blocks is groups of experimental units that are similar. Randomized block designs means you separate the subjects into blocks and then randomly assign treatments within each block. Matched pairs design is a very special type of block design. So they're paired and then you're basically flipping a coin to see who gets what. Or you can actually do a before and after. So that's another special case which we really haven't covered today. Then we did the check for understanding. We had a political strategist would like to design an experiment to compare the effectiveness of 3 different YouTube advertisements promoting a specific presidential candidate. She's going to use 300 randomly selected YouTube users for the experiment. So describe a completely randomized design to compare the effectiveness of 3 advertisements. So you can see that this is, you have one block here. Now, someone did ask me, they said, isn't this a block design when they saw this drawing? Well, it's actually just a completely randomized experiment. So if you go and you look, well, we don't have the drawing on this one, but if I go to the notes before, go to page 17, where I have my, see, that's basically, except the difference between the picture here and the picture here, let's go back to it, is that I'm just getting 3 treatments. It's not 3 blocks, 3 treatments. and or 3 levels of the treatment, and the treatment is an ad. All right. So it's one treatment, which is an ad with 3 levels. All right. And that's why I made that little note there, is to make sure that we understood that. Okay. Now, if we wanted to do a block design, what we could do is we could kind of rank the people from young to old, right? And we could have the oldest 150, they get their own experiment, okay? And the youngest 150 gets their own experiment, because we do react differently to ads. I know I was joking that I can get the day I was teaching this, the day before I taught this lesson, I was trying to show someone something on my Facebook, another teacher, and it's lunchtime, right? And I go back to my room and I go to get my phone. Well, my phone is still in my backpack because I hadn't touched it since I left the parking lot that morning to come teach. And I know that's not very common for our younger types. So there is a difference between younger and older in terms of media consumption. I'm not saying I don't play with my phone. I do. But I'm not as attached to it as younger people tend to be. All right. So why might a randomized block design be preferable in this context? Well, the whole point of a block design is to control for a confounding variable. So this is a really, to control age as a confounding variable. This is a really important point, okay? Within each block, there will be lower variability of results, making it easier to determine which ad is the most effective. So that is identifying the confounding variable. Make sure you identify what you're trying to control for when you do a block. So that comes to our next problem, which is this 2007 free response question from the AP Stats exam. It's dog joint and hip health. As dogs age, diminished joint and hip health may lead to joint pain and thus reduce a dog's activity level. Such a reduction in activity can lead to other health concerns such as weight gain and lethargy due to lack of exercise. So one thing you might notice, they're saying as dogs age. Oh, age is a confounding variable, right? Or it can be, right? It can be. Well, actually, but we're not going to do it here. Sorry. But we're trying to, age is an issue. So it is in a way a confounding variable. I take that back. And we'll talk about that in a second. And what we're worried about is reduction in activity. Reduction in activity, the effects are weight gain and lethargy. So they're trying to test 2 dietary supplements, glucosamine and chondroitin, to figure out which one is better and reducing the onset of canine osteoarthritis. So they'd probably be measuring, does the dog have arthritis or not? Researchers will randomly select a total of 300 dogs from 10 different large veterinary practices around the country. All dogs are more than 6 years old. So they're trying to, minimize variation a little bit. Their owners have given consent. That's good for an ethical reason. And they're going to evaluate the changes. So this is what they're measuring, the changes in joint and hip health after 6 months. So they said, what would be an advantage of adding a control group in the design of this study? Well, actually, that reminds me of a question someone asked when we're doing this problem. The very first one right here. Shouldn't we have a control group? Well, sometimes here, we're definitely trying to make sure all kids get SAT prep, and we are fairly certain that SAT prep will help them get a better SAT score. So why would we doom some students and tell them, no SAT prep for you, you have to take it straight. And darn if you get a lower score, that's who cares. All right, here it's asking, it doesn't have a control group, so they're just giving them one or the other. So why would it be helpful to add a control group here, but it wasn't so much over there? Well, again, here's the problem with control groups. It is true, the control group gets a 0 level of the factor of the treatment, right? So they're not going to get the glucosamine or the chondroitin. They're just going to be normal. Well, why might we want to do that? Well, I'm pretty sure SAT prep helps you get an higher SAT score. Do we really know that chondroitin or glucosamine really help joint and hip health? So the answer they have here is a control group gives the researchers a comparison group to be used to evaluate the effectiveness of the treatments. The control group allows the impact of normal aging process to be measured with appropriate response variables. The effects of glucosamine and chondroitin can be assessed by comparing both of these to the control. So do these two supplements actually help? All right. So that the advantage is, so what's this E and the P? Well, you can either get an E, a P, or an I. If you get an I, it's like no points at all. You can actually get a 0 points on a free response question. All right. Your goal is 4 points, but you can get 0. So let's try and not do that. So if you describe the advantage in the context of the study, so look at what's the context here. Let's go ahead and make that more of a hot pink. Oh, look, we talked about the actual drugs. The impact, oh, that's on joint and hip health. That is context right there, okay? So, assuming a control group is added to the other two groups in the study, explain how you would assign the 300 dogs to these three groups for a completely randomized design. It's kind of funny, it's 300, we were just doing 300 here. All right, if you drew something like this, all right, these are very nice, but they don't fully answer this question. What is this question asking? How would you assign? The 300 dogs. So that means you actually have to give instructions on how to assign. So actually, let me go ahead and make that a different color. How would you assign the 300 dogs? So here's their answer for part B. Each dog will be assigned a unique random number 0 to 100 using 0, 1 to 300 using a random number generator. Now, I always think this is kind of a weird way to do it, but okay. So you're going up to each dog, and somehow, to me, this seems like a hassle, but okay. You're like, okay, your dog 50 and your dog 37. So we're using a random number generator, or better yet, I would use the numbers on slips of paper. Mix it well. Then I don't have to worry about, oh, I already called that number. So I personally would use a hat with the numbers in it, right? So this is one way. I'm going to add another way to do this, all right? So each dog will be assigned a unique random number 001 to 300 using a random number generator on a calculator, stat software, or a random number table. The numbers will be sorted from smallest to largest. The dogs assigned the first 100 numbers in the order list will receive the glucosamine. Then the next 100 get the control, and the last 100 receive chondroitin. Okay, personally, what I would do is I would number dogs from 1 to 300. Use RNT to generate 100 unique random. RNT is RNG, random number generator. That's and I'm only typing it because I would write random number generator, but I'm short on space to generate. Actually, personally, I'd use a hat. Put numbers in hat. This makes it easier and mix well. Draw 100 numbers without replacement. If I say without replacement, that means they're unique. These get, what do they get? I don't know. What did they give them? The glucosamine? Glucosamine. All right. Draw another 100 numbers without replacement. These are the control group. And rest are the chondroitin, which I'm probably going to misspell, chondroitin. All right, so let me make that, so I'm going to move this over here. Actually, I can just move this down. Let me just move this down a little bit. So that's the scoring criteria, and this is personally how I would do it, because I think that one's a little easier to do. So there are different, so this is alternate method. But this is fully accepted. To me, it just feels weird. All right. So I personally think the hat method works really well when you're trying to do 3 groups. If you're doing random number generator, it's nice because you can say 100 unique numbers without, no repetition. But when you do a second group, you might have some. So it gets a little messier. And I'm talking from an actual practical drawing number standpoint. Okay. Oops, I'm jumping to the last part. Now, part C, rather than using a completely randomized design, one group of researchers proposes blocking on clinics and another group of researchers proposes blocking on breed of dog. How would you decide which one of these 2 variables to use as a blocking variable? So we're trying to decide, do I block on breed or do I block on clinics? So there are 10 different clinics and I don't know how many breeds, but just assume that we know how many breeds. So which one is going to minimize the variability? Well, if you got Great Danes, those are like giant dogs, right? Let's see. So you got dog breeds. Let's go look up dog breeds, right? Dog breeds. Look, there's all these dogs, right? And I'm going to tell you that probably the bulldog, I don't know. I bet you they have lots of joint issues. Border Collie, probably not so much. Dachshund, probably, yeah. Chihuahuas, you got to be careful with those. So I personally think the dog breed is the bigger factor. So let's see what they said. The key question is, which variable has the strongest association with joint and hip health? The goal of blocking is to create groups of homogenous experimental units. It is reasonable to assume that most clinics will see all kinds and breeds of dogs, so there's no reason to block on clinic. On the other hand, different breeds of dogs tend to come in different sizes. The size of a dog is associated with joint and hip health, so it would be better to form homogeneous groups of dogs by blocking on breed. Okay, so I was like, why did I see that? So you get an E if you relate the stronger relationship to joint and hip health. Pretend I typed it. Let me fix that. Joint and hip health should be used as the blocking variable, in this case breed. Or you state the variable with a larger anticipated response should be used as the blocking variable to make groups as homogeneous as possible. As homogeneous as possible is the goal. Here, let me do yellow, right? And the variable with the stronger relationship to joint and hip health. That's how you get an E. Now, if you just say create homogeneous groups, and you have an error in the application, you get a P. If you do not acknowledge there may be more variability with one compared to the other, that could knock you down to a P. If you don't recognize that both variables are associated with variation in the response variable. So in other words, does clinic affect dog and hip health, right? The effectiveness, or does breed? And it should be pretty clear it's breed. So there's the walkthrough of what we did on E3 when we started going further and deeper into experimental studies.